Another thing that was tried and dismissed as silly was the resonant wire pressure sensor. This works on the principle that if you get a guitar string and you strum it, it makes a noise, which you can pick up using, if it's an electric guitar, you can pick it up using a pickup. If you then stretch that guitar string, it makes a different noise. The pitch changes, and you can pick that up using the pickup. So basically, you could use a guitar string to measure pressure. People actually built these things. People actually ended up calibrating these things. Luckily, we're in a world where these things no longer exist, hopefully, except for maybe a few sites in WA. Now, the next one we'll look at is the capacitance one. Some of you may have old books that show things like capacitive cells, and they'll show cutaway diagrams of capacitive cells. I'm not going to bother telling you any of that, because all of that is old-fashioned rubbish. You don't need any of it nowadays, because for the last 24 years, we've had the ceramic capacitive cell. Now, what the ceramic capacitive cell is a piece of ceramic, like dinner plate. It's about as thick as a dinner plate, and it's about as tough as a dinner plate. Now, you might think, well, you can drop a dinner plate on the floor, but compared to the old-fashioned metal pressure cells, it's very tough. You can hit it with a screwdriver, it won't break. It probably, if you attacked it with a hammer and chisel, you could break it, but that's about it. These things are great. The ceramic itself, it shows the ceramic bending here. The ceramic itself only moves by a few nanometers. So there's hardly any movement in the diaphragm. This cell is attached to atmospheric pressure, so this is a gauge pressure cell. If we wanted, we could fill this in here, and then we have an absolute pressure cell. The fact is that the ceramic pressure cell has completely revolutionized pressure measurement. Nowadays, we use a capacitive ceramic pressure cell, unless there's an incredibly good reason why we don't. And that good reason has got to be something like it's over 400 degrees C, or it's over, I think it's something like 2000 kPa. So you must have extremely high pressure or extremely high temperature. Otherwise, you use a ceramic pressure cell. In the old days of using the old metal pressure cells with the wires coming out, the old metal ones, you used to have two for every installation. One to be installed and one to be in the factory being repaired, because they would go wrong all the time. Basically, I have seen these go wrong. The old metal ones, I've seen them go out of calibration because the operator cleaned it with a hose pipe. I've seen it go out of calibration because the operator wiped it with a rag. Anything could make the old-fashioned metal ones go out of calibration, whereas the ceramic ones, you can wash it with a pressure hose, you can scrub it with a wire brush, and it's not going to go out of calibration. So, strangely enough, you can get high-pressure ones which are metal-clad, and they do have metal cladding across them, and they are, although the metal does protect it, they do suffer from a slight problem in that if you do hit it with a screwdriver and you succeed in making a little hole in it, then it goes out of calibration. So although the metal-clad ones will survive higher pressures and higher temperatures, they're a bit more vulnerable to being attacked by screwdrivers and wire brushes. But having said that, there really is no excuse not to use a capacitive pressure sensor. There really is no excuse not to use one of the old-fashioned metal pressure sensors. The only place in the world that still uses them is WA. And I'm really trying to change that by telling people to stop doing it. These were invented 24 years ago by a firm called Endress and Hauser, which means that 4 years ago their patent ran out. So now every firm is making capacitive pressure sensors, and there is now no excuse to not buy one. This is what the ceramic itself looks like. It's nowhere near as thick as that. It's actually, in real life, the whole thing is about that big, and it's about that thick as well. So if you imagine it's about this thick, it's about that thick and about that size looked at across. Oops, messed that up, didn't I? Get rid of that. So that's about the physical size of the thing. And it just lasts forever. And even if you do manage to damage it, you change it yourself. You don't need to send it back to the factory. If you need to measure differential pressure, then you have two ceramics pressure sensors back to back. And now we can measure differential pressure. We never have to worry about it going out of calibration. We never have to worry about it being damaged by an operator. In the olden days, if we wanted to measure a tank level, for instance, so if I've got a tank, I would always say to people, okay, what you need to do is you need to get a differential pressure gauge and you need to pipe it to the tank. And the reason I used to say pipe it to the tank was because when the DP cell breaks, and it was a case of when it breaks, you could change it without emptying the tank, because you could just close a tap in the pipe and change it. I would never ever advise anybody to use what was called a flange-mounted DP. A flange-mounted DP mounted on the side of the tank like that. And the reason I would never advise anyone to change it, because I knew that when the diaphragm went wrong and the pressure sensor went wrong, you had to drain the tank. Nowadays, with ceramics, I would certainly advise you to use a flange-mounted DP, because any pipe that we have connecting is a maintenance item. Any pipe that we have connecting will get an airlock sooner or later, or block. Oops. Any pipe we have connecting will get an airlock or block. So nowadays, with the state of reliability of ceramic pressure sensors, I would say flange mount onto the tank. You'll never get an airlock, it'll never get blocked, and if it does ever get dirty, the operator can clean it with a hose. Different types of, the ceramic pressure sensors come in all sorts of mountings. You have the differential pressure, the flange mounted, there's several types of flange mounting, and you also have the ones such as this one and this one that are set up to measure differences in pressure at different parts of a tank. If you have a closed tank, you need to know the pressure at the top and the bottom, and these two types will give you those two pressures. I have heard that very, very hot sulfuric acid has been known to slightly discolor the ceramic. But apart from that, these things are great. Oh, another thing to mention, they're cheap. They are reasonably priced. They're actually cheaper than the old-fashioned metal cell type things that they're replacing. And of course, with these, you only have to have one of them, because you don't need to have one in the factory being recalibrated. Now, just as a matter of interest, how am I going for pace here? There's a couple of pace buttons. Does anybody want me to speed up or slow down, or are you happy? Okay, I'll carry on at this rate then. Right, wherever you have capacitance, you always have inductance, because somebody always thinks it's going to be a good idea. For some reason, somebody decided to make an inductance pressure sensor. I wish I had a picture of them. Hopefully you never get to see them apart from in a museum. They are horrible. They were dreamed up by some nutter on a very bad trip. And they've got levers and pulleys and bits that you have to adjust, and you have to adjust this and you have to adjust that. They are just awful. And the only thing you need to do with them, if you find one, is take it out and put a capacitive one in. That'll be the end of it. Now, moving on to piezoelectric. The way that piezoelectric works. This uses crystals, and a thing about crystal, one of the unique characteristics of certain types of crystal. If I get a crystal, there's a tube of crystal. Inside a crystal, the molecules inside the crystal, the little crystals, are like tiny little batteries. They're like tiny little batteries, loads and loads of molecules, all like tiny little batteries. And like tiny little batteries, they've got a plus end and a minus end. Now what I need to do is plus there, plus there, plus there, plus there. Now when they're all randomly pointed, you don't get any electricity out of it. But if you smack this crystal on its end, for some reason, called the piezoelectric effect, if I suddenly smack the end of that crystal, all of the little batteries line up. Now, each one of these little batteries produces hardly any electricity. Each one of these little batteries produces about, a quarter of a poofteenth of a volt, right? But when you've got thousands and thousands and thousands of them all lined up, then what we end up with is 20,000 volts coming out of one end. That's a lot of volts. So what you can do is, we can make a mechanism that looks a bit like this. You've got a plunger, and that's on a big spring, and that is a target, and then that's inside a case, and then you have another little catch here, and that's on a spring. Okay, and then the crystal itself lives here. Now what happens is, you push in on this end, and then eventually the pressure of you pushing in overcomes the spring on this little thing here, which is a catch. And then what happens is, this plunger rushes forward, causes this hammer to smack into the crystal. It then makes a clicking sound, and a big spark comes out of the end, which goes off and lights your barbecue. That's a piezoelectric lighter. I'm sure you've all seen the things. You push it in, it goes click, 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 makes lots of sparks, big fat sparks, lights the barbecue. If you stick your finger in there, you get a big fat electric shock. Ow. Now, that is a great principle, because we can use that to measure pressure. And we use that to measure pressure is the piezoelectric pressure sensor. The nice thing about the piezoelectric pressure sensor is it's what we call well conditioned. A relatively small amount of pressure produces a massive amount of signal. So piezoelectric pressure sensors are great at measuring pressure. The problem is, they're really great at measuring changes in pressure. With your barbecue crystal, if you keep it pushed in, you don't continually get 20,000 volts out of it. You get one lot, and then it needs resetting. That's the same with the piezoelectric pressure sensor. It's great at measuring a change. It's absolutely fabulous at measuring vibration. So they're great for measuring things that vibrate because they give a lovely signal out. They're not very good at measuring a continuous pressure because, the truth be told, the only thing they actually measure is changes. They measure acceleration. They're very, very tough. They'll take massive pressures. They'll give a lovely signal out, but they're not good at measuring continuous pressure.